So this is going to be from Vinodh Chellamuthu from Utah Tech University, and they will be giving their talk on increasing STEM students' retention rates using mathematical modeling and curriculum design. So I will give the floor to them, and I look forward to another wonderful talk this morning, or this afternoon, rather.
Thank you, Rachel. Just a quick question. We got 2 minutes to noon. Can we start the presentation, or we have to wait for 2 more minutes?
It's up to you. We can wait a couple minutes if you'd like, or you can get started with an introduction, whatever you prefer.
Absolutely fine. Yeah. Hey, thank you so much for coming to the talk. I really enjoyed the previous talk given by the 3 people. That was awesome. Great job. So I'm going to talk about something which I do in my classrooms, and I never have done sortal study. This is one of my sortal study I started with, and the focus here is I would like to check how the differential equation concepts you can relate to real world scenarios through mathematical modeling that could impact student confidence and the mathematical abilities. And also it's a twofold purpose, because differential equation can impact students at the junior and senior level after they get the basics of it. So how does that impact the STEM majors? Are they going to be on track for STEM majors after taking this class, or they're going to be disappointed, or it's too much of work? So that's one of the things. And also I want to point out this sortal study was supported by a program through AMATIC. It's called Project SLOW. I'll talk about it later. So why I want to do this, I want to give a brief background about my university first. I am at Utah Tech University in St. George, Utah, and it is an open enrollment, open access institution. What does it mean is we accept everyone, the ACT scores, or it's open enrollment, so we accept everyone. So, and also we grant associate degrees, bachelor's degrees, and master's program now, and also a doctoral program is coming up. So the idea is when students come in, when they get associate's degree at that around mark, this differential equations class actually serves as a capstone project kind of thing for the first 2 years of college mathematics. So that is the reason I would like to see how this class, when you incorporate mathematical modeling, does that affect their retention in STEM after the 2 years of mathematics classes. And it is also important to think, because every time when you do a problem in mathematics, the common question I receive from my students is like, okay, where is it used? So that is a common question I receive. So this is mathematical modeling is one of the best ways where you can actually incorporate real world scenarios to show where that is used. And another thing is like, it helps them to see multiple applications in diverse areas, even within their own majors, for engineering, biology, so they could see that, oh, mathematics is used in all those fields. And obviously, when I engage students in conceptualized context learning, it really provides an opportunity for them to learn more and inspire to study on different fields. So those are the reasons why I want to pursue this sortal study. And how I did it is I gave a pre-test and a post-test survey after every unit, and there was an end of semester interview after I posted the grade. And then I checked these 2 scores, and I did this study during the weird semester of pandemic. I started the study in spring 2020, and then the March 20th, the pandemic hit, and then the schools are closed. So all I'm going to share is what happened before the March 20th and the end of semester interview. So, but that can give an idea on how students are thinking about incorporating mathematical modeling and giving real world scenarios within the perspective. And my sample size is, I got 20 students in the class, differential equations, and I will talk about how I did that pre and post survey. And this is a syllabus which is available in SIMIODE webpage. and I just mimicked that idea. But one of the thing is I gave a pre-test one, which is before I cover the first order differential equations. Uh, and I will share the survey questions. And then after they do the modeling activity, I again give a post survey after the modeling activity and see how that has changed their perspective towards STEM fields, or how they change the perspective of getting a confidence in solving mathematical problems. So that's what the idea is. And the design was to have this for throughout the conceptual things, but I'm going to share only for first order differential equations. So if I really want to show you, this is an example I put after I teach them the first order differential equations. This is a home eating problem, which is one of the problem in SIMIODE. So I just took it, and I'm going to show you work, the student work, exact student work. So you will see some mistakes here and there. So I will point out that what is the thought process of the student is itself. So before that, I would like to point out what is the problem we are going to solve, the mathematical modeling problem. If you, when someone is taking a vacation over a Christmas break for a total of 4 days, what is the best option? Is it really leave the furnace thermostat on at set it to 21 degrees Celsius, or they can set in such a way that it can turn off after some time when they turn it off, and then it turns on again at some time between the 4-day period? And which one is economical to keep the house warm or to reheat it? So that's the question. And I like this approach in so many ways, because this doesn't give a student saying solve first order differential equations, not putting a problem. It is a word problem. They have to figure out what they have to do. So there are steps, guided steps for them to do. The first step is they say solve one. There's the equation is given. That equation number one is given to them, and then the initial condition. And I want to point out the y of t is the temperature inside the house, and then the a is temperature outside the house. So that's what that is. So that is the temperature of the medium. They have seen already this T minus the temperature of the medium. That is the rate at which the house temperature is going to change. So students know how to solve this. They use variable separable, and then they get a solution. But the point is, if I just give this problem, they may not know what is the K means, what is the parameter A means. So all those things are giving them a picture of it. So they have to really understand that perspective of it. And then the exercise 2 was given in such a way, asking, okay, here's the K value, here's the initial value, like, because when they're leaving the house, the temperature is 21 degrees Celsius, and then we got to go with what are the units of K and what's going to happen if you just leave it that way. So if the students can solve it, because y of 0 is the initial condition, at 96 hours, what's going to happen? And if they really don't do anything, that's where when they come back, it's going to be pretty cold. So students could understand, okay, why this is important through this. And now comes the point, they say, okay, you reheat the house like for the entire 4 days. That is the R of T, and they say that is constant. But again, the assumptions are coming in. Nothing is constant, because it's going to change every hour, every 2 minutes, every minute. But on average, we're assuming that it's constant. And then students solve for it, and they found the long term what's going to happen. And you can easily see there is a mistake in this slide, and that should be e to the power negative 0.001. So, but when you take a limit, you are approaching 0.21. That is your R naught. So we got that cleared out. And then phase 4 thread is a good way to have a qualitative things of what's happening. And then this is exactly what my students think about it. Okay, what's going to happen long term when they took a limit, and what's going to happen? There are several mistakes in this, but I just want to point out how the students are thinking about it. And the exercise 5 is, this is when you're not turning, like you're actually turning on, like you're leaving it on for 4 days. So that's where the integral is coming in. My students are going to ask, okay, why I need to use integral? Because they need to know they can use calculus 1 to find the total energy, and then or not they found was 0.21 from the previous exercise, and then they integrate that throughout, they get 20.16. And I will talk about one of the things, how the students are thinking about the unit towards the end. And when now comes the assumptions, up to exercise 5, it is just like leaving it on. So, and then the second scenario is what happens if you switch it off and then turn it on before 96 hours. That's what exercise 6 means. So we are assuming there should be some time T1 before 96 hours. The furnace the thermostat should turn on, so that when they come back, it should have 21. That's what the goal is. So they're going to have the same process. They do the variable separable, all those things. And then if they calculate it, that's what that is. And then again, I'm not going deeper into mathematics itself. My talk is mainly focusing on how this has helped. So I know mathematics, we all can do it here. So the example is coming from the SIMIODE. So here, there are two scenarios. The first scenario is we are finding what's going to happen when we want, after coming from 96 hours, we want the temperature to be 21. So we are setting that up and solving it for C, the constant C, and then we got it. And we should understand, on average, the furnace is actually pushing in the energy at 3 degrees per hour. Again, this is an average. It is not, we are assuming that way. And then we know if it is going 3 degree, that is a linear scale. So we have a linear equation, and also the house temperature, red is going down. That is not a linear, but that is meeting at a point T1. So we are solving it for T1. That is at approximately 91 hours, the thermostat has to turn it on again. So once we get it, then previously we accumulated all those, we calculated from 0 to 96 hours of that 0.21, the constant rate of thermostat is coming in. But now here, all we need to do is, we're not using it from 0 to 91 hours. We are turning it on again at 91 hours. So at 3 degrees per hour. So once you do it, then you get 12.614. Now the students can compare this to, and they know the energy from scenario 1, where you are not turning it off, you're turning it on throughout the 96 hours. And the other scenario is you are turning it off and then again turning it on after 91 hours. So the energy wise, the best economical strategy is to turn it off and then turn it on again. But you can notice one thing in the slide. You see the student actually put a dollar symbol here. And because whenever there is someone going to say cost, the student thinking, okay, cost is always dollars. But in this case, it is not dollars, if you think about it. It is actually like the unit of energy. So that's one thing I noticed all my students are thinking about, thought process itself. So once I do all this, and as I told you, I have given a pre-survey. This is the pre-survey I have given to them, and that's the results you can see in the graph. And you can notice that most of the students do not know what the first order linear equations mean in terms of real life scenarios. And then after that modeling activity, which I explained to you, I gave the post-test. This is on all the questions, it's actually changed it. And for example, participating in modeling activities made me to understand how first order linear equations are utilized in real life situation. So I was very happy to see this result, because I was expecting it. That's my assumption, but I can see it through data, which was good. And then after the post-test 1, with the pre-test, I got only questions, whereas the numerical score questions. And then the post-test, in addition to the survey, I also gave them like a free writing handwritten questions, like they can say whatever they want. I asked all these 4 questions. I told, okay, write down one thing you learned from the modeling activities, and write down one thing you're still unclear about first order, because I need to know what they are unclear so that I can address that in the next class or in the upcoming classes. And I also would like to know what they liked about the modeling activities and what they disliked about the modeling activities. So here are the responses. These are all coming from my student work directly. You can notice that one other thing they say is like, I learned just how much these equations can apply to real world, because previously they just stop right there, the equation. They do not know, oh, this equations actually simulate a real world scenario. So those are great. And sometimes I still don't know how to tell if it is first order. So then I went back to the class and I actually showed them some examples. Then they know, okay, here's a degree matters, all those things. And this is one thing I want to talk about. Write down one thing you disliked about the modeling activities. The ones we do at home take a lot more time than I expected, and I fell behind. So this is a common thing, right? If it is just a problem, they can easily do it. But that's not going to help them, because after they graduate, none of the employer is going to ask, okay, go to do problem 5 from chapter 5, I'll give you $5,000. Nobody's going to say that. It is like they have to really understand the scenario and use the classroom knowledge to solve the messy problem in real life. So that is a common thing. What is one thing you disliked about the process? But they appreciated why it is important. And this is another problem. As part of the post test I just gave a scenario deliberately and told, hey, is this equation could model the temperature of the cake in the hot oven? So, and I said, do you think the student equation models the cooling of cake well? Please explain why and why not. And they could do some improvements, I asked them. And I was really happy to see these responses, because they said this equation cannot model the scenario, what was mentioned. And they really gave one simple example. They said the model does not even involve T, the temperature of the cake, so which is good. And are there any improvements? They clearly mentioned, again, they didn't really say just the equation itself, okay, dt over dt equal to k times t minus tm. They didn't really say that. They explained that why and what happens in the scenario to have this equation is correct. So those are very important observations that I really made through the study. And as I mentioned, I want to know the well-rounded approach of this. And this was done during the pandemic semester. So I have to do everything online after the month of March. So I asked my students after the final exam, is there anybody who would like to be interviewed to complete the study? So they said 8 students really said, okay, they are willing to spend. They're super nice. So I asked this question: what are differential equations? Why are they useful? This is just like after they have taken the differential equations class, after I graded the final examination, I posted the grades, and this is the question I asked. And I said, tell me everything you know about mathematical modeling, because I would like to observe what they are saying and how confident you are solving differential equations. All those questions really made them to think when in the interview process. And this was not given before the interview. It was actually just asked during the interview. And 7 of the survey participants indicated that mathematical modeling activities push their thinking beyond the textbook problems, which is very important, because if they are really stuck with the textbook problems, they get more comfortable. But after they graduate, it's going to be an issue for them, like thinking beyond the textbook and thinking out of the box. So that's one reason why I can easily see from the interviews. And one other thing I asked about in the interview was, tell me one example where you could connect differential equations. And that was during the COVID-19 semester. And everybody immediately said, hey, you could do system of differential equations SIR model. That is after the differential equations class. You could do that. That was awesome. And again, overall, I felt like the students actually had a great exposure to real world scenarios through mathematical modeling, and they studied better the differential equation scores through this approach. And the impact was they were able to explain the parameters in the differential equations and its physical significance. That's very important. What do you mean by K? What is T? What is Y? What is all those things? That's very important because nobody is going to say that when they graduate or when they go to the upper division classes. Like, it has to be like they need to make sense of those. They need to build their own models. That is important. And majority of the comments really made lots of sense to me. And I didn't see not many negative comments, and they all stayed touch with me after the semester, which means that they like the course, which is great. And many stated that hands-on activities we do with this kind of things outside the textbook really help them with their learning process. And also, they indicated that they could stay. They are going to stay in the STEM field. And I know by at least not collecting data, the students who actually took my class in spring 2020, now they all graduated with STEM degrees, and then they are working in a workforce right now. So, which is great. And an important takeaway for me, again, as a teacher, I would like to learn. I would like to improve myself through those experiences so that I can better serve my students. So it really helped me to think more deeply how my students are thinking. And then through this experience, students can make important connections among mathematics and other STEM fields, and which in turn created a positive impact on their interest of taking mathematics and applying to their significant majors and all those things. And I cannot really agree more. Differential equations is a critical point where STEM students choose their interest and proceed with their mathematical adventures, or they will probably say, no, it's not for me. So it is very important to include hands-on activities like authentic learning, active learning, all those things in differential equations class. And one of the things I'm currently working on is how to take modeling, mathematical modeling activities into calculus curriculum. The challenges are there is lots of differential equations, not many sections, but calculus classes, you have many sections. So that there is a transfer agreement articulation with other universities. So those are the challenges we're facing. But you honestly, including mathematical modeling activities within the calculus curriculum would be fantastic. And I'm working with another person, Keith Knabb from Piedmont Community College. We are talking about it, and I think we hope to get something done through that. And I would like to really give a big shout out for Amatic Project Slope program because they supported the study and they helped me throughout all those things. And here is the fantastic people of my team. And without them, I would have not done anything. And I would stop here, and I would love to answer any questions if you all have.
How many students do you have, or how many sections of differential equation classes you run?
We have only one section of differential equations class, and the study was done in the class of size 20 students. 20
students.
Yes.
Okay. All of these students, are from the engineering, or are they anybody from outside of the STEM you allow them to join, or maybe economics, or things like that?
So they are, whoever is going to take a math minor, they have to take this class. And in this particular class, if I remember correctly, there was one finance major who was a math minor, so he was there.
Okay.
And there was one biology major, okay. Outside the STEM, if I want to say, there was one finance major and one information system major. There was only two. Yeah.
Information system, okay.
Yes.
There is no biology students shows up in this kind of classroom?
Yeah,
I know
since
it is in STEM.
since you asked me if it is non-STEM, STEM, yes, of course. There are lots of biology students in this class. Biology students,
Okay,
computer science students.
okay. Yeah, well, even though many schools, I mean, I'm not talking about the top level schools and medium-sized schools and colleges, they basically don't show up. Very few students show up only unless they are applying to go for STEM.
Yes, I agree. I totally agree. Thank you for the question.
Yep, thank you.
Any other questions?
How do you send this message to, I always like to send these messages because I also do the consulting in industry. This is one of the questions we always ask. How do you promote our, differential equation is the crucial point where the
Yes.
STEM area one, even in the AI, machine learning, these are some of the very important area coming up. How do you promote this, this message to grow that?
Within the students population or within?
Yeah.
Okay. So one of the things I do in my campus is I get the business, industry, and government agency projects from local
Correct.
agencies, and
Uh-huh.
I try to bring those examples within the classroom.
Okay.
And there is a follow-up course after this. If they are really liking the mathematical modeling aspect of differential equations, I have a follow-up mathematical modeling course. We are a little bit fortunate. We got a new degree program with applied on computational mathematics.
Great, excellent. Thank you for your answer.
Thank you.
Okay, well, thank you so much, Vinodh, for your talk. That was amazing. And thank you all for being here and for your questions.